Good morning, everyone. My name is Theolodat, and I'm AMO physicist by training, now working at Quantum Machines in the customer success team, whose goal is to help our customer achieve their dream experiments with our products. And although we are working with all the qubit platforms, today I'm going to focus on a very serious candidate for QPUs that are neutral atoms. And here you can see a very nice picture from Quera Computing in Harvard, representing their 256 qubit simulator. Now, neutral atoms QPUs have a very large variety of advantages, such as high scalability, high fidelity, and fast gates with very long coherence times and so on. But at the end of the day, the full hardware and software stack for the control is quite tedious to develop, and it takes a lot of time and effort to scale it up. And so this is the reason why at Quantum Machines we aim at bringing a new paradigm in quantum control with the Quantum Orchestration Platform. So this is a fully integrated hardware and software system that allows you to run the most advanced experiments on any number and types of qubits using a super intuitive programming language called Qua. I should emphasize the fact that the compiler here takes care of the translation between Qua code and FPGA language, so that you don't have to know anything about FPGA to run even the most complex experiments. And for instance, you have a fully parametric waveform generation. You can acquire the waveforms using analog inputs. You have real-time processing with very complex arithmetic, so not only additions and subtractions, but also trigonometric functions, power laws, and square roots, and so on. And there is also a full control flow with while loops, for loops, if statements, switch cases, and so on. And all of this enables real-time feedback, meaning that the outcome of a measurement can update the running sequence on the fly. And so you can perform active reset of the qubit state or atom arrangement with Rydberg arrays. And so this is what I'm going to present now. On the sketch on the right, you can see a standard atom array experiment where the atoms are inside the vacuum chamber that has several optical accesses for the cooling and imaging beams and the static traps. And the CCD camera images the array, which has been randomly populated after cooling and trapping of the atoms. And it transfers it to an image processing unit represented by the FPGA stack here that will retrieve the initial occupation matrix and passes it to the OPX using fast analog readout. Then the OPX can perform the sorting logic and derive all the trajectories to rearrange the arrays into an arbitrary target matrix defined by the user. And the last step is to generate multitone waveforms which correspond with the corresponding chirped frequencies and send them to the acousto-optical deflectors in order to generate and move the tweezers and perform the sorting. So I should mention now that we are working on developing a new product called the Observe that will interface the camera with the OPX and perform the image processing and transfer the data very efficiently. So we have estimated an overall 50 microseconds latency on a 32 by 32 array, which is a state of the art. And there are now a few prototypes that are working, and we are collaborating with different labs and camera manufacturers in order to be able to release it as soon as possible. And for now, let me show you the first step, which is how can we transfer the occupation matrix using analog readout. The idea is very simple. Once the FPGA has derived the occupation matrix, it will send a TTL signal to the OPX that will trigger it to start measuring and integrating data coming into one of its analog inputs. And this value is then compared to a pre-calibrated threshold in order to assign on the fly the reconstructed occupation matrix and put zeros and ones whether there is an atom or not. And the code shown in the snippet on the right is the real code that we send to the compiler and that is executed on the hardware. It's not pseudocode, although it looks very much like it. So you can see how easy it is to program in Qua. You have the while loop, this wait for trigger function, you measure and you can integrate the data. And then you can have this conditional statement to assign variables with different values. So once we have retrieved the full occupation matrix, we can start deriving the standard row by row sorting logic that can again be nicely written using qua macros shown here in the snippet. So again, it's not pseudocode, it's a real program that we'll send to the compiler. So I'm not going to enter the details of all these complex calculations. I just would like to emphasize the fact that all of these calculations are executed on the hardware level with a fixed and known latency. So for instance, here for deriving the logic of the 7x7 array, it takes only something like 10 to 20 microseconds. And this is deterministic, it's known. And of course, more complex logics that move the atoms between rows, for instance, can also be implemented this way. So as an example, now I would like to show you very quickly how we can play waveforms using the quantum orchestration platform. So first, after having derived the sorting logic, we want to ramp up the tweezers' amplitudes adiabatically. For that, we use Blackman shape that has been preloaded to the device. And we can update their amplitude on the fly, that you can see in the play statement here. And the element called colon represents a single frequency that is generated by one pulse processor. And on the OPX, you have 18 pulse processors that are completely independent, although they are phase synchronized, in a way that you can sort a 16 to 16 atom array with a single device. And of course, you can combine several OPXs in order to scale it up. Then we want to chirp the frequencies of each tweezers in order to move the atoms from their initial location to their target destinations. And again, here with a single play statement, we can on the fly update the amplitude, the duration, and the chirp rates of the pulses. And after the atoms have been rearranged, we want to ramp down the power adiabatically in order to place the atoms into the static trap. And this is done again with the Blackman pulse. So in order to convince you that all of this works, let me show you a very short demo where here the output of the OPX is connected to an oscilloscope that displays both the time trace and its FFT. And in this example, 9 tones are played simultaneously and chirped to one direction. So it's like putting all the atoms to one side of the array. So it's like the simplest sorting algorithm that you can think of. Although what is important to note here is first that the amplitude of each tone remains constant over the chirping, and also that there is no skirts around the tones, which shows that the phase is preserved and that there is no dead time during the chirping. So this works quite nicely. And indeed, very recently, we connected an OPX to an atom-based QPU in Mark Safman's lab in the University of Wisconsin-Madison, where we successfully sorted atom arrays, as you can see in the pictures here, that are real array pictures. The whole connection and implementation only took a couple of days without any need for complex characterization or optimization. So we could realize sorting of a 7x3 array or 3x3 at the center with different regions of interest and so on. So this was very smooth and easy to implement. And I should emphasize the fact that here we only used 1 millisecond chirped pulses with constant linear chirped. So here, for instance, on the left, you have the spectrograms of each of the waveforms that have been sent for each row. And you can see the linear chirps. Now, in a future release that will be released in a couple of weeks, there will be the possibility to create arbitrary frequency chirps with piecewise linear approximations that will allow to implement the minimal chirp trajectory schemes. And this will considerably reduce the pulse durations and increase the sorting fidelity. So here in this example, we have chirped pulses that last only 200 microseconds. And you can see these minimal chirp trajectories that are well reproduced with the piecewise linear approximations. And again, since this type of trajectory is polynomial, it can be very nicely written in the few lines of qua comments that's represented on the snippet on the right here. So with this, I hope that I convinced you that we can very easily perform neutral atom arrangement with the quantum orchestration platform.